Okay, here we go. I hope you see my slides. So as Jean said in that first part, I'll talk about the tools you need to run deep learning and AI workloads on Power Systems. So all the software you need, how to install it, and also a big part of about our recommendations on what to use, what tools to use. So first, I'll talk about the OpenCE, Open Cognitive Environment Toolkit, which is basically everything you need to maintain a software stack for AI on Power. So I'll explain how to build it, how to use ready Conda channels. I'll mention then containerizations, why we advise to use it on Power Systems, so what are the advantages, how to build simple images, what web IDEs you can use. So I'll show that in demos. And finally, I'll conclude with useful software that it's good to have in your toolkit to run distributed trainings, to optimize hyperparameters, and so on. So all these slides will be available at the end. I shared the link. So I voluntarily embedded a lot of links and code samples in it for you to use. Okay, so let's start with OpenCE, Open Cognitive Environment. So it's a software distribution that includes pretty much every software you need for AI applications. So it includes all the deep learning frameworks, TensorFlow, PyTorch, Pandas, MXNet. It includes all the data science libraries you might need, Pandas, NumPy, Scikit-learn, and so on. And it includes, finally, the NVIDIA software, the underlying NVIDIA software to run it. So CUDA toolkit, which provides CUDA. You have QDNN, you have Nicol, you have DALI, TensorRT, and so on. So all that is free and it's free and open source. It's hosted on GitHub, as I'll show you just after. And it's a good tool to help you build and maintain your software stack on your system. So it's provided on that link. Let me show. So I keep switching between environments. Here. Okay, so you have everything available on that GitHub link. So let's go here. So basically, it's a list of recipes that you see here to build all these packages. So we see PyTorch Lightning, we see ONNX, TensorBoard, and so on. So it's a list of source to images with integrated recipes to build it, and to build it in a Conda environment that I'll mention later.
Sorry, John, we have a question in the chat on NVIDIA Rapids, whether OpenCE includes that.
No, it's not included anymore. It was included in Watson Machine Learning Community Edition, so the previous release, but it's not supported anymore, at least for now. It's not in the OpenCE. I don't know if it's planned to be in there. Okay, so as I just mentioned, it was previously called Watson Machine Learning Community Edition, WMLC, and before that, IBM Power AI. And the major difference between WMLC and OpenCE, which was released last year in September, I think, it's that it's a shift from IBM support to a community-based support. So it means that the community, we have large clusters of contributors. So the most famous ones are the Oak Ridge with the Summit supercomputer, which is the second largest supercomputer in the world. We have a cluster at the MIT, which is named Satori. We have the Oregon State University that has a cluster too. And they all maintain these recipes. And basically, we have a comparison in one of our internal presentations that I find relevant, is that we used to provide ice cream, and now we provide the sugar and milk and everything you need to cook ice creams. And now it's the user that has to cook ice cream, and that's the flexibility to cook any ice cream they want and adapt the recipe. So that's basically the philosophy of OpenCE, to have a more flexible workflow. And as mentioned with Rapids before, we have a few features that has been dropped, at least for now, which are Rapids, SnapML, and large model support, which will be covered by Jean right after. Let's have a quick look at the release cycle. So the current version is 1.1.3, and the basic idea is that there is a release a new release of OpenCE should include a new release of both TensorFlow and PyTorch. So it roughly follows the release cycle of the major projects. And what you have to keep in mind about a release is that a release is a set of versions of softwares that are guaranteed to work with each other. So that's what we see on the right. You have the uncoordinated upstreams, which are all the packages that are developed independently. So you have one stream for TensorFlow, for PyTorch, and so on. And they're gathered in one OpenCE release, which means they're guaranteed to work with each other. But that doesn't mean at all that a new release of a package won't work. Matter of fact, it usually does. So this means, on that example, that you can have that release of OpenCE, the top one, and when that new blue package is released, you can install it and see if it works, and if it works, it's fine. So you're not constrained anymore by releases, and it's a flexible way to have a continuous flows of updates provided. Okay, that's all I wanted to mention. Okay, let's have a brief look at the software requirements. So it runs on Red Hat 7.6 or higher, on Ubuntu 18.04 or higher, Python 3.6 or more. So you have to install the NVIDIA GPU drivers when using GPUs on your AC922s. And that's the only software from NVIDIA you need to install. Everything else will be provided in Anaconda repositories that I show right after. And so you basically need to install Anaconda. You have the versions below. Okay, and now let's have a look at how we use it. So as I briefly mentioned, OpenCE is packaged in Conda. Conda is an open source package manager, which is not only for Python, but in that case, we use it for Python, which helps you manage software stacks, to resolve dependencies, install software. And its main interesting feature is that it has environments that can isolate software stacks. So you have the link of the Anaconda installer right below. Make sure you use the PowerPC compatible versions, because they're all quite mixed on that website. And okay, so you need a Conda channel to install your packages. So you have two options. As I said before, OpenCE is provided for you to build it. But the good news is some people already built it for you, for everyone, and made some channels publicly available. So that's the case of that channel that is built by the MIT. They build it for the Satori cluster, and they make it available for everyone to use. So let's have a look at that channel. Okay, so here I'm on the web interface that lists the packages, and we see that they already built everything in that. So we have TensorFlow, version 2.3.1. We should have also 2.4, maybe 2.4.1 here. We have PyTorch. We have NumPy. Oh, NumPy isn't the main package, sorry. So basically, we have everything that is included in OpenCE and ready for you to use. So that's my advice, at least at start, is to use that channel. There's also another channel that is built by the Oregon State University, which seems to me a bit less up to date, but not that much. So it's worth having a look from time to time if you're looking for a package. And of course, the alternative of that is to build your own Conda channel. So the problem is that you have to host to build the channel, to host the channel somewhere for your users to use it, the same way the MIT does. And the advantages is that you're autonomous. You're not dependent on the MIT to provide releases. So those are the two ways. What I did not mention is that in the MIT, you have also a documentation tab, which is a great place to find information in that documentation. They explain basically everything they do to run workloads in their cluster, and there are a lot of interesting informations. For example, in the WMLC on OpenCE section, You have all their installation guides on how they configure their systems, the Conda channels, how they manage environments. So that would be worth a read if you're interested in that. Okay, and as I said, the alternative is to build your own channel. So we'll briefly have a look at how we built it in case you need it. Okay, so those are the screenshots I mentioned that okay, so let's go with this one. So if I go on the OpenCE GitHub repository, you see you have the main OpenCE repository, which is here, which contains all the recipes all the code to build a feedstock. A feedstock is a repository containing a package. You have OpenCE environments. So this contains the releases and some subsets of OpenCE in case you need only PyTorch and PyTorch-related packages, for example. And finally, you have all the repositories, the feedstocks, where the packages are developed. And to build a Conda channel of OpenCE, it's fairly easy. Let me switch to my slides. Okay, you have that here. So basically what you do is, obviously you install the requirements I mentioned before. You have to git clone that OpenCE environment. You have to pick one environment file. So let me show you that again. The environments are here. Environments. So basically we have one environment for OpenCE, which contains everything. So it's a dependency, so it includes all the other environment files. And you have single environment files, so in case you want to build only a PyTorch stack, you can use that PyTorch environment, which contains a lot less package. So we see PyTorch and QDNN and some other stuff, Torch Vision. Okay, so the drawback is that if you want to build the whole OpenCE, it takes a while. It takes like 10 to 15 hours to build the complete list of packages. It's a lot faster with smaller environments, so it depends on what you want to do. If you want to have everything, you can build everything, and then you can have smaller environments if you want for testing purpose, for example. Okay, so that's basically how you build OpenCE. And once you've built it, it will produce a Conda build directory, which is a Conda channel. So it contains all the archives of the packages you built, and you can use that as a Conda channel to run install commands of your packages. And that's the directory you'll want to expose on a web server if you want to make it available on multiple machines. So that's basically what the MIT did. And the OpenCE build part is pretty flexible. So you have the options to build single packages, single feedstocks. You have the option to test environments once you build them, which is a good thing to do once a build is complete, because each feedstock defines some tests in their code that are automatically run if you run the test of command. And finally, you have options to build inside containers. So the OpenCE will spawn a container in which it will run the installation code, which makes it less system dependent. You don't need to have a clean server with a stable software stack to make sure the build will work. In container can be a good option to have that out of the box. Okay, so that's basically for the build part. You'll find a lot more information. So in the GitHub repository, if you need to actually build it, you have everything in the README of that main OpenCE repository. So you have the requirements and everything here. Okay, so let's switch back to that. And now how to use Conda channels. So let me show you that on an actual container. So this is a container I host on my system. So to configure a channel, it's pretty easy. You have to run conda config, prepend the channel, channels, and then your channel URL. So in that case, you can use the MIT channel that I put here. Oops, sorry, I put here. You can use your local Conda build if you have built it locally. You can use your own Conda channel through an HTTP server. So you're free to use it. And so I won't run it as I already done that. Now, once you have done that, you can use Conda as a package manager, as you might know. So you have Conda search to search for packages. Try that with NumPy. So should find all the available versions of NumPy. You can run Conda install NumPy to install NumPy. You can optionally specify a version equal, I don't know, 1.18.5. That command would downgrade my NumPy to 1.18.5. You can remove packages with Conda remove. So pretty basic stuff of a package manager. What's really interesting with, okay, so let's mention GPUs first, sorry. So as I said before, you have to install the drivers on your host system for the GPUs. And then the Anaconda default channel provides a package that is called CUDA Toolkit, which matches the CUDA version, so 10.2 or 11 for the latest ones. And it includes everything needed for apps to run using GPUs. So you have CUDA runtime, you have NVCC compilers, it embeds profiling tools such as NVSite. So basically everything you need. And let's search that. It. And you see it's provided version 9, 10.2, or 11. Okay, and the next great feature about Conda is the ability to make environments, which means to make isolated software stacks and have multiple software stacks on the same system. So that's what I do here. Let's take Conda en list. So you see I have all these environments. So I have, for example, a particular environment that I use to run Horovod code. I have the active one, which is OpenCE, my main environment, and I have other things. It depends on the versions. And for example, it allows to have multiple, as I said, multiple software stacks to work with each other. For example, in that environment, I have a Python 3.7. And if I switch another environment using the activate function, okay, so now you see I'm in the Horovod environment on the left. And in that case, okay, so it's the same Python, red, maybe in Dask. Okay, same everywhere, great. I think I have environments where I have the recent one. Okay, no. But basically, you can have multiple environments and have multiple Python versions, multiple TensorFlow versions, and have all of them work independently on the same system. So that's a great way to have each user have manage its own software stack and not be dependent on dependencies of other projects. You can easily create environments using the Conda create command. So you specify a name with -n, and then all the packages and optionally the versions you want to install. Okay, so that is basically how to use Conda and Conda environments. And one last comment that is useful that I want to show you is Conda info, which shows you everything. So so you have the Conda version you installed. You have the channel URL. So here we see that I configured the channel of the MIT on my system. We see also where Conda stores the environments, where it stores the package cache, and so on. Okay, so that's it for Conda. So as I mentioned, Conda info. Okay, and finally, I put the links of the old WMLC channels. So before it has moved to OpenCE, those are not maintained anymore, but you might find in them some packages that are no longer supported or that not yet rebuilt for OpenCE. So if you're looking for a package, it's worth having a look in one of these channels in case your software is provided there. And finally, so let's say you're searching all these channels and your package is still not available, the package you need. So you still have the options to use pip inside Conda. So you have pip is a Conda package, so each Conda environment which have its own pip. And you can use pip to install packages. So the drawback of pip is that if there is a binary file for that package that is built for the PowerPC architecture, it will be installed and it will work fine. And if not, it will try to install it using the setup tools file it finds on the registered GitHub of that package. So I said a drawback, but not really, because most of the time it works, but that setup.py might not work for PPC64LE. And in that case, you would have to recompile the package manually. So as I put in the warning, it will conflict if the same package is installed through Conda. So my advice would be to always search in Conda first, install through Conda, and if not found in Conda, try with pip. And if not found in pip, try to recompile the package manually using the instructions of the website. So if you do that, if you try to recompile, a good thing is to try to build a will file. It's a .whl files, which are pip packages, self-contained pip packages. And you can then save them and make them available for multiple users, added to your channel, the channels you built, and so on. Okay, so that's it for the okay, I quickly mention the case of AGAP system because it's not trivial. So it's a case where you want to have access to packages on a system which is not connected to the internet. I'll go through it very briefly because I'm not sure it's your case, but it's still here if you need it. The issue is that you can't just build OpenCE because everything is not in OpenCE. It relies also on the main Anaconda repositories. So the idea is to think ahead of about your stack, the stack you want to build, and you create a custom Conda channel for that build. So you'll need an internet-facing system, and basically the flow is to clean the cache of Conda, install everything you need. That way you have all the archives in the cache directory, and then you export that cache directory to your AGAP system, which is not connected to the internet. You have to run Conda index on the directory, and that will create JSON files, which are Conda metadata, to make it searchable as a Conda channel, and then use it locally on your AGAP system. So that's pretty much the flow. It's a bit complicated, but it's still the easiest way we found to do that kind of thing on systems that are not connected to Anaconda repositories. Let's go to the second part, where we talk about containerization. So we use them extensively on our clusters in Montpellier. The advantage is that it allows us to really isolate users on our system. So we have multiple clients that are working on the same servers, all isolated in containers. We can set resources limits, in particular GPUs. So on a 4 GPU server, we can say that we have 2 customers with 1 GPU each and 1 customer with 2 GPUs. And it allows clients to be really isolated, to build their own software stack as they see fit in their container, without harming any other work from any other people on the server. So on top of that, we run these containers on the container orchestrator, which is Red Hat OpenShift, so based on Kubernetes. But this can also be run as in standalone mode, perfectly fine. And I'll show you right after the advantages of doing so. So I don't know any OpenCE ready images. So we have the old WMLC images, but I don't think it's really necessary to use them, because basically it's just an Ubuntu container with Anaconda already installed. and a bunch of stuff with licenses about WMLCs that you won't need. So my advice would be to go from start and build an image. So I did a few tests, and you'll see it's pretty easy to build a minimal image that will work. So basically, you start from an image. I picked Ubuntu, and you just wget the Anaconda installer, run the installer, configure the OpenCE channel, and then create environments before starting the container. So that's a very minimal working example of a Docker file. And following that, you can add install any libs you need through apt, through Conda. You can add services running, so an SSH service for users to remotely connect. And you can add GUI services, web IDs, for example, which I'll show right after. And that's what we do in Montpellier. Let me show you that. So as I said, so the environment I used in the terminal right before is in fact in a container. And in these containers, we run web interfaces for users to connect. So that JupyterLab interface is running inside the container, and it allows me to run Python notebooks, to open terminals, to manage my files on the left, to have extensions, to have dashboards. So it's really a small development environment for users, and it's really convenient for running notebooks. And you see I have access to GPUs. So that container should have 2. Okay, so I see I have 2 V100 GPUs. So it's running on a 6 GPUs server, and I have other people using the server at the same time. So that's basically the first interface we use. So I have it. So yeah, I just showed that in that capture. So you can run a terminal, you can split screen and have notebooks on the side. You can have multiple Conda environments for the notebooks. So it's pretty convenient to quickly develop some code. Installation is, let me get back to my slides from the beginning, sorry. Yeah. Okay, so installation is pretty convenient. It's just JupyterLab is available in the Conda repository. So you just install JupyterLab and Node.js as a requirement. And then you start that in the CMD of the Docker file. So instead of running a small bash that does nothing in that example, you can run a JupyterLab interface. So you have to expose the right port for the container, and then your users can connect inside the container through the interface and work directly from there. And another great interface, even better, I think, that we use is that one, which is called Thea, which is really a web version of Visual Studio Code from Microsoft. And it's really, really powerful to explore files on the left. You can open terminals. So I'm still in the same container. We have both interfaces running in the same container. So I still see my 2 GPUs. I can easily edit files. For example, have a look at that one. I can add extensions. Not sure I have any installed, but you can search the VSX registry for extensions. Here you can see that I'm running in my Horovod environment, but you can switch Conda environments, switch repositories. No, sorry, I'm in the Horovod directory, but I'm in the OpenCE Conda environment. And here I see my Conda environments available. One last great thing about it, it's just like any IDE, is that you can run the debugging. So for example, in that script, I can say I add a breakpoint here, switch to the debug tab, run debug mode. And so the running will start, and it will stop right at my breakpoint. And here I can explore. So I see I'm inside the call stack of the function f. I can explore all my variables that are set here. So basically, I have X. I'll show you that code later, but basically, you have an X variable local that is 0.58. You can add watch expressions. So you let's say you can check if X is greater than 0.5. Okay, sorry. So let's say X 0. Okay, so here it's 0.58, so it's false. And then I can run. It will call F again, and so on. So like any debugger, and it's a pretty powerful interface to use in your containers. Let's have a look at how we install it. So this is here. And the install is pretty much the code that is available in the documentation of the product. So you have to, so it still relies on Python 2. So you have to create a separate Conda environment, which is specific for Thea. Install the npm package manager and build Thea from here, and then add that in the CMD of the Docker file. So that's basically what we do in Montpellier. We have a Docker file here. I put the link in the previous slides, so we can have a look at the start, which is the file that is run for the Docker file, and we see. So we set a bunch of variables, but here we see we start the Thea interface, and then we start the JupyterLab interface, and both run on the container. Okay, so let's switch back to the slides.
We have a question in the chat again. How might that work with Slurm on Bede, or do you recommend everyone to use interactive nodes?
So Slurm is the scheduler that is used. So
Slurm is a kind of batch scheduler. So you submit tasks to be done. It's not interactive. So here we are talking about more, development environment. So really, when you want to interact with your code and develop on the machine, debug and so on. So and also run or create and explore Jupyter notebooks. So it's a different task, I would say. Slurm is really for heavy background tasks or jobs that you want to submit that will last in days, while TR or Jupyter notebooks are just for code exploration and development.
Right, and you can have multiple Docker images running. One interactive with interfaces for development, and one the same without the interfaces, just to be instantiated by Slurm to run workloads.
But then that's right. You have to bear about the resource allocation. So if you have one dedicated TR environment, it will lock the GPU for this environment for sure.
Right. Okay. And to conclude on containerization, so we really advise to use them for development needs. It really allows to effortlessly make multiple users collaborate and each have their own stack and feel free to install whatever they need and still keep the host environment stable. Think about if you use containers, it's good to use CI/CD pipelines. So on our side, we develop on GitLab and we use GitLab CI/CD. You have also GitHub Actions and also multiple others. And the idea is really to simplify the development workflow. So in our case, it automates every time a new release is pushed to master. It automates the build, the test of the image. And if the test is successful, it's pushed to the OpenShift registry for the users of OpenShift. So basically us, we provide images to clients. We can use that image to instantiate instance on the cluster. And one final thing I wanted to mention, although it's still not compatible with Slurm, but still for the interactive part, you have Jupyter Hub, which is a multi-user tool to instantiate single-user Jupyter notebooks. So basically, you have a Jupyter Hub which can instantiate on-demand Jupyter notebook. So basically, any Docker image you tell Jupyter Hub to use, and then each user can connect to its own instance and shut it down when it's done working and start it again. That way, you don't always book the container doesn't always book the GPU, but only when the user wants to start its own instance. So it could be a nice tool to consider if you want to run that kind of work. Okay, and I have one last part. See, I'm a bit running out of time, but I have one last part about useful software it's good to have in mind. The first one is Horovod. It's a deep learning, distributed deep learning framework. So it interfaces pretty easily with any framework, TensorFlow, PyTorch, so on. And it's based on the MPI library to communicate. So to communicate on the control side, and for the data, it uses Nickel, which is an NVIDIA library compatible with MPI, but optimized for GPUs. But you don't really need to know that, just that it's included in the latest release of OpenCE. And basically, it doesn't require much code to run. You just have to initialize Horovod, set the current process to use the local rank. So that way you ensure that you have one GPU per process. You have to make the optimizer distributed, but it's just a wrapper about your own. So that's a Keras sample, but it's just a wrapper about the Keras standard optimizer. So no big code modifications. And you just have to register one callback just to ensure the initialization of workers is consistent. So that's basically how we use Horovod, and it's pretty convenient to run trainings on multiple GPUs and even multiple nodes. So you run that with Horovod run, which is a wrapper about MPI run. The syntax looks the same if you're familiar with MPI. And the benchmarks, so those benchmarks are from x86. I don't know any of that big benchmarks on Power, but we see that the scaling of Horovod is really quite impressive. It scales up to more than 500 GPUs with like 90% of the idle case for Inception or ResNet models. So it's a good tool to have in mind if you want to run distributed trainings. The next one is Dask. Dask is a parallel computing library, so it can allow code to scale to manage data sets that are larger than memory, and it also embeds a distributed task scheduler in case you want to scale multiple nodes. But that might be better to use Horovod for that. So I'll focus on the larger than memory data. So what it does is it embeds APIs that are just like the familiar ones from Pandas, from NumPy. So you see it defines a Dask data frame, which has almost the same values, the same functions as the Pandas data frame, which allows a data frame to be bigger than the memory available. And same thing for NumPy below. And I think I have an example of that is better. Let's have a look at Dask. Okay, here I did a simple notebook. So I define a random NumPy random Dask array, which is a wrapper about NumPy arrays. And you see that my array is of size 800 gigabytes, so it's way bigger than my available memory. Let's have a look. So yeah, I have a bit more than 500 available gigabytes of RAM available. And still, I can use so functions like sum, like in NumPy. So it sees the resulting array, which will sum by line. So you get 1 million by 1, 100,000 by 1 array. And what it did so far is that it just described a graph of the operations it wants to run. So it says it has to instantiate that X variable and sum it through columns, but it hasn't done anything yet. And when you call the compute function, it will run that graph and compute that. And you see that it will effortlessly be able, so as it's quite big, it takes a bit more than a minute. But you see that, so the RAM starts to increase, the used part of the RAM starts to increase. But you see that it will be able to compute the sum on an 800 gigabytes, so bigger than my RAM array, without actually allocating everything. So what it does is it allocates chunks. So here I define chunks of 8 gigabytes. So it will allocate multiple chunks and do the operations chunk by chunk in parallel. And it will manage to work with arrays that are way bigger than my available RAM. So let's wait while it finishes. And for the while it computes, you can have a look at the last library I wanted to mention, which is Scikit-optimize. Scikit-optimize is a hyperparameter optimization library. So it's a kind of a plugin of scikit-learn, but it's not limited to scikit-learn. You can optimize any function. And the nice thing about Scikit-optimize is that it embeds Bayesian optimization algorithms, which is not the case. So you have multiple options to optimize parameters. You can do random search, you can do grid search, you can do gradients exploration, and so on. But Bayesian optimization is adapted in case you have a complex function, which is a black box, so no gradients, which is expensive to evaluate. So you can do thousands of tests, and in which observations are noisy. So typically, a neural network training. And what the code looks like is that you define the dimensions you want to explore. You define your functions. So here I have my functions f, which does some complicated stuff with sinus, tangent, and so on. You define an optimizer, and then you have a simple ask and tell interface. So ask will query the optimizer to propose new points of your search space, which you define in dimensions, to explore. Then you do your computation. So here we compute f. And then we tell the optimizer, this is the result, and then compute the Bayesian optimization and give me new points. Okay, so that it's what it looks like. So in that case, I have my red function, which is the function we want to approximate, which is the real function. And the green space is step by step what the Bayesian optimization feels like, the range in which it expects my red function to be. So you see red points are the points it samples, and the goal is to minimize my red function. So in that case, it's in 1D, but it's for the example. And we see that step by step, it picks new points, either by trying to improve the good points it already has, or by trying to reduce the points where they have a big uncertainty, so where the red zone is big. So in the first 2 or 3 steps, it tries to reduce the big green zone. Then it tries to explore about around 0.8, where it feels like the minimum. At some point, it starts to explore again, so it reduces the big green zone on the left, and so on. And finally, it converges to the minimum it is looking for. So that's a 1D example, but you can do a lot bigger example. And this is an example from an actual example we run with the client. And another nice tool about Scikit-optimize is that it can draw plots like that of the optimization. So you have codependencies graphs in color. So in each color, you see how 2 variables influence the result. So the best result, so the minimum we found is the red star, and all the black points are the points we tried. So each black point is actually a neural network training that took 2 or 3 hours. And on the diagonal, you see that it tried to isolate the importance of each variable. And that's a really good tool to see which variable have an impact. For example, we see that variables like command D rate, the first one is very flat, so it has no impact on the on the actual performance of the model. So we can say that we can fix that. In the other case, we have variables like the global mean merging value, the bottom right, which have a high impact. And those are really great options to really understand what are the parameters impact, and to understand better the influence of them and get rid of the useless one, for example. And finally, let's switch back to my Dask demo. So we see that the RAM came back at normal, and it computed in 100 seconds. So my array, which is truncated, of the sum of each line. And you can, of course, combine all of them. You can imagine that you have a training which uses larger than memory batches, so you use Dask. You want to parallelize that on multiple systems, so you add Horovod. And then you want to optimize the parameters of that training, so you can wrap that in a Scikit-optimize example. So I haven't done that demo yet, but that might be a nice thing to do. And that's it for that first part. Thank you for listening to me.